I'm here with Craig Proctor-Parker. I'm accident specialist in Durban, South Africa, and he's going to be explaining some concepts to us that is often used in an accident type of environment. So the first thing we're looking at is a total station, and this is used to record different distances. So essentially how it works is there's a laser that's shining from the total station, and the laser shines off, bounces off a mirror, and then it reflects back, and then it's read by the total station itself. So the distance is identified by looking at the time it takes for the laser to go to the prism or the mirror and reflect back. And from that, the distance can be calculated, and then it's also divided by 2 because it's the time traveling from the total station to the prism and back. The trigonometry can be then used because it's at a different angle depending on the angle of the prism that's being used, and then so with trigonometry you're able to identify then what the different distances that has been recorded. The important issues that need to be taken into account is that the height of the prism is actually fed into the total station to be able to get that specific recording, because obviously that is going to have some effect on the readings. And in the zero position of this base is considered, or the base of this total station is considered over here at the bottom of the total station. And some total stations have got GPS units mounted on top of them, so you're able to then identify exactly where that location is. So this is your zero homing position that you would then be measuring from. So what we're going to do is we're going to be doing quickly a demonstration in terms of taking different readings with the prism, and then from that we will be able to then map out a layout with this special software that's being used. Okay, a total station has to be calibrated every year. Why is it important to have it calibrated?
Well, in terms of using the measurements that we get from this to compile a drawing, and then being able to pick up from that drawing various measurements, perhaps the width of a vehicle or the height of a vehicle or the distance between objects. When we go to court or that drawing is used, the basis of that drawing is the measurements that we've picked up from this device. So we have to be able to have a certificate for the device to say that the certificate is within a specified parameter of tolerance, whatever that may be, 0.1 of a millimeter or 1 millimeter. So generally we would have this calibrated once a year, and it is held once a year as a certificate. If for some reason we drop the device or damage it or suspect it for some reason that it may be out of calibration, we may even send it in an extra occasion to have it calibrated.
So this measuring wheel is able to measure the distance that it travels. So all that you have to do is you push it around and it's able to see the distance you've gone.
You can basically import data from a total station. If you measure by means of a total station, you can import data into here and then it'll plot all the points. You can take manual measurements and plot them and draw your plans to scale. You can import images from Google Earth onto here and it scales it automatically. So your drawings will always be to scale. That's very nice. You can do 3D imaging. So this is a case I'm busy with at the moment. It's a top view. And we can just click on 3D and we've got the drawing in 3D, which we can also just tilt it up and down, turn it any way we want, left and right. We can go back, we can go forward, right up to the vehicle.
And that's a horse and trailer.
Horse and trailer that's jackknifed and gone off the road. We can actually go look all the way around and we can position the vehicle. It just gives a better perspective of the evidence on the road.
We have done quite a few reconstructions of accidents over the past few years, and obviously there's a requirement for certain measurements to be done. Why is it important that these measurements are performed accurately?
So we stress this to any personnel that go to an accident scene for the reason that the application of the measurements is in order to get an outcome. So for instance, we may be trying to determine the speed of a vehicle from a typical deceleration calculation. So we would need to know, as a very basic indication, the length of a skid mark. If we've measured that length of the skid mark with the total station, it needs to be accurate so that when we apply that in a mathematical calculation, we know that it's accurate. By the same methodology, if we're doing a momentum exchange calculation, we would need to know where the point of impact and where the vehicle has come to rest, the distance that the vehicle has moved, whether that's in a straight line or whether it's plotted along an arc. We've used the total station to measure that, and therefore we need to know that those measurements are accurate so that when we apply that to the calculation, we know it's accurate.
And obviously, when you're in a port situation, those measurements and the accuracy of those measurements is then quite critical.
Correct. So one of the things that we would need to do when we go to court is exactly as you mentioned earlier on. We start off with the very basics to say, we took the measurements, that's the device we used, it's a calibrated device, here's the certificate for it. We imported that through the appropriate software and programs, and we can follow the chain to the court to show that the measurements are accurate and what we measured is accurate, and then apply that into the calculations. So the whole process of the measuring, the principle of measuring, from beginning right the way through to its application is accounted for and is accurate.
With the accurate measurements, these are entered into a computer simulator, and over here it's able to be seen how an accident happened and how a motorbike was hit by a vehicle.
But when it comes to corner weight scales and having to measure the weight of the vehicle, why is it important to know the center of mass of the vehicle?
So in the investigation of any accident, you may, for instance, be dealing with the rollover of a vehicle. Now, in order to determine, calculate factors of rollover, you would need to know the lateral position of the center of mass, the height of the center of mass, or the fore and aft positioning of the center of mass. Now, that position is generally known in the vehicle, but in order to get that accurate, we would need to have the vehicle set up on a set of corner weight scales. We'd need to know the distribution of the weight, and then through knowing those and through certain procedures on the corner weight scales, we can accurately or quite accurately determine the center of mass of the vehicle, and those values for the center of mass are then applied into a calculation that would allow us to determine things like the static stability rollover factor. It is also allowing us to determine a center position of the vehicle, center of mass position of the vehicle, when we applying that in momentum calculations so that we know we are applying to an accurate position on the vehicle.
And then obviously there will be factors that will influence that center of mass, such as the number of people that are in the vehicle, where they might be sitting in the vehicle, the amount of fuel you've got in the vehicle, maybe some luggage or other things that are being transported, and that obviously would also have an impact on those calculations.
Quite correct. So in the process of measuring, again, it's not just measuring, it's making sure that when we measure as accurately to the parameter as possible. So for instance, if there was only a single driver and the driver weighed 80 kilograms, we would put an 80 kilogram bag in the driver's seat, or get a person that weighs 80 kilograms and put them in there. So we would try and apply the principle of measuring through the corner weight scaling as accurately as possible.
A vehicle was parked on 4 scales, and then the readings on each scale was measured, like over here, the left front and left rear, and then there's also right front and also the right rear values are taken. Then the vehicle is jacked up, and it's jacked up as high as possible. And as you can see, only the front wheels are then on the scales while the back wheels are not. And then a measurement is taken in terms of how high the rear axle is from the ground. Once we've done all the measurements on the vehicle, we need to jot down some values. And so these values that we're going to be jotting down are going to be shown over here. So essentially, we have to take the 4 readings from the 4 scales when the vehicle is flat in this position. Okay, so when we did it, we found that it was the front left corner was 319 kilograms. The front right corner was 340 kilograms. The rear left corner was equal to 200. And the rear right corner had a value of 195 kilograms. Okay, so these are the values that we obtained from the scale. The vehicle is flat on the ground, all 4 wheels are on the scales. And then what we then do is, with these 4 values, we're adding up together to get a total weight of the actual vehicle. And in this case, it equals to 1,054 kilograms. Okay, now there's another 2 values that we had to take into account. So when the vehicle was in this position where it was lifted up from on a rear axis, so it was only the 2 front scales that actually then it got a reading. And so we have to take that into account. Okay, so for us to do that, we need to take the 2 front wheel values of those scales and record that. And when we did the test, we found that it was the 1 wheel, which was basically the front left corner, that had a value of 332. And then we had the front right corner, which gave a value of 343. So we add those 2 together, and that becomes a total of 675 kilograms. Okay, so those values are the ones that we've obtained. Now, some other values that we need to take into account, which you would be given due to the fact that this is standard on most vehicles, and but you could also be measuring it. The first value that you need to take into account is the track width. So the track width is the distance between the left and right hand side tires. So here it's 1.463 meters. Okay, so for us to take that into account, that would be this distance over here. That's 1.463 meters. The wheel base, that's 2.47 meters. That's essentially the distance between the front and rear axis. Okay, so that is 2.470 meters. Wheel height, and in terms of what's the height of the wheel up to the tire height, this is something you could probably measure. So that would be that distance over there, and we will be recording, or we actually recorded that to be at 330 millimeters. Now the problem comes in is that the reason we want to take that into account is we need to know the distance that this axle is from the ground, and that would be half of that wheel height. So if we had to put a marker and a cross over there, that would be half of that. So that's equal to 165 millimeters. Okay, so now we're able to know what the height is, and the reason we need to know is that because the center of gravity that we're going to be calculating is going to be from the 2 axle points in terms of that height. It's not going to be from the ground height itself. Okay, and then the other bit of information is quite critical that we need to take into account is the vertical height raise. So when the rear axle was lifted up in the air and only the 2 front wheel readings were taken, that height over there had to be taken into account. So that height over there was measured to be 545 millimeters. yet something needs to be taken into account. It might be that, but if theta is over here, between those two lines that we want to take into account, we've got to subtract the axial height as well. And that we found to be 165. There's 165 over there. So essentially, we are going to be saying, well, this height over here, if we can take it across over there, this height over here will be equal to 145 minus that 165. Okay, so that will give us our actual height that we've got. And if we do that calculation, we get 545 minus 165, and that's equal to 380 millimeters. Okay, so what we have to keep in mind is that the height that this rear axle needs to be lifted up needs to be in such a way that this theta value is between 15 to 20 degrees Celsius. Oh, sorry, between 15 and 20 degrees. The problem comes in that this is essentially what we would like to achieve, but it is difficult for us to be able to lift the rear end of the vehicle that height. It is quite a large angle that one needs to lift it up with. Some people will say you need to try and lift it up with about 600 millimeters. Again, it all depends on a jack that you're going to be using to jack up the vehicle. Because keep in mind, you've got to jack it up at the axle of the rear wheels. You can't jack it up anywhere else. So for these calculations to happen and for them to be accurate, you need to jack it up over there. So you try and get it as high as possible, with so that you can fall into these restrictions. Not always possible to do. Like you will see with this example, lifting up with 545 millimeters off the ground actually gives you an angle that's way less than 15 degrees. But we've got to take that into account, and it allows us to still get a relatively close value to what we want to obtain, even though it might not be the most accurate reading we want to have. Okay, so essentially I'm going to be leaving this over here just as a reference for us. Well, yeah. And then what I'm going to do is then do the calculations next to it. So essentially there's 3 center of gravities that we need to obtain. We need to obtain the center of gravity that's going to be the along in terms of from the front to the back. So we need to know if you had to move from the front to the back where that center of gravity will be. And that will be along this center line over there. We also need to know then where would be the center of gravity from left to right of the vehicle. And then we need to obtain the center of gravity in terms of in height above the ground of the vehicle. So these are all things that we need to take account. So if we have to look at center of gravity from left to right, that will be in that sense, or that over there. And in terms of the center of gravity in terms of height would be way about in terms of height on this specific aspect, or it could be in terms of height of the vehicle over here. So therefore there's these 3 values that we're going to be calculating. Because the first thing I'm going to be doing is I'm going to be trying to find out in terms of the center of gravity moving from the front to the back. So along this axis over there, where along that axis would we find the center of gravity? Okay, so to be able to do that, we are going to be looking at these following equations. So the front mass percentage needs to be calculated. So essentially what we do is we look at these values that we've recorded. And these recordings is the front left corner and front right corner. This is now when all 4 wheels are on the ground. And we go and we then go and say, well, the front mass percentage what percentage of the weight is then distributed to the front axle. Okay, and for us to do that, we say that's equal to 319 plus 340. So those two values over there. We divide that by the total mass, which is 1054, and we multiply that by 100. And that gives us an answer of 62.52%. So 62.52% of the weight is in the front of the vehicle, which makes sense. I mean, your engine is usually in the front of the vehicle. That's your heaviest part. Unless you have a massive fuel tank at the back, most of your weight is going to be towards the front. Okay, then we need to calculate the front to rear position. So we want to basically know where about would this position be. And that's got to do with the wheelbase. So we're basically going to be looking at this wheelbase between the axes and identify, taking into account this distribution, because keep in mind that we took the readings of the scales underneath the wheels. So those are like our reference points. So our wheelbase is equal to 2.47. And we multiply it by the decimal front mass percentage. So we take this front mass percentage we got, divide by 100, and we get our decimal front mass percentage. So that's 0.6252. Multiply that together, and we get an answer of 1.544 meters. Okay, now that we've done that, we need to determine where the center of the vehicle is. In other words, where's the center between these two axles? And for us to be able to do that, we essentially take this wheelbase and we divide by 2. Okay, so wheelbase is equal to 2.470. Divide that by 2. And we get an answer of 1.235 meters. Right, and then essentially what we want to determine then is what distance from this center line that we've now just calculated is 1.235 meters, which would be roughly over there. And if you had to correlate it across to the top view, be roughly over there. What distance from that line are we going to be having this center of gravity value? Okay, and for that, we have to say, well, the distance is equal to the half wheelbase, which we just calculated over here. And we've got to subtract the front to rear position. Okay, so that's equal to 1.235 minus 1.544, which we obtained over there, and that is equal to negative 309 millimeters. Okay, now something to keep in mind. If we've got a negative value, it implies to the front. If we've got a positive value, it implies to the back. Okay, so because we've got a negative value over here, it implies that this is therefore 309 millimeters to the front. Okay, so 309 millimeters from this center line to the front will indicate that we've got our center line that is roughly over there somewhere. So that distance over there is 309 millimeters. Okay, so now we've got it on the axis from the front to the back. We know where the center of gravity is, somewhere on that line over there. Okay, so now that we've done that, we need to now look at the center of gravity from the left to the front. Okay, so essentially we're trying to sort of see, well, we know the center of gravity is somewhere on that line over there, but is it towards the left-hand side? Is it towards the right-hand side of the vehicle? And how far? Okay, so a very similar process is going to happen now. In this case, we're going to be looking at what the left mass percentage is. Okay, so left mass percentage, essentially what we're going to be doing is we're going to be taking the total left mass values. So over there, that would be the front left corner and the rear left corner values. That's 319 plus 200. Okay, so we essentially have to take those values divided by the total mass and then multiply by 100. Okay, so that's equal to 319 plus 200 divided by 1054, and we multiply that by 100. And that equals to 49.24%. Okay, now we need to determine left to right position. Okay, and again, it's a thing of where we take the track width, and track width we've determined as 1.463. That's the distance between the left and right hand wheels, and we multiply it by the decimal left mass percentage. So this percentage value we just calculated divided by 100. Okay, so that's equal to 1.463. Multiply that by 0.4924, and that gives us a value of 720 millimeters. And now we need to determine what our half track base is, or our half track width is. Okay, so that should be width. So essentially, to do that, to know where the center of the cart is equal to our track width, and we know our track width is equal to 1.463. We divide that by 2, and that gives us a value of 731.5 meters. Oh, sorry, 0.5 millimeters. Okay, now that we've done that, we need to determine the distance from the center line where the center of gravity will be. And again, we take half track width, which we just calculated over here, which is 731.5 millimeters, and we subtract the left to right position, which we calculated over there, 720 millimeters. And that gives us an answer of 11.5 millimeters. Now again, if this value is negative, it will imply that it's towards the left-hand side, so to the left. If this value is positive, it will imply that it's to the right. Okay, so since we've got 11.5 millimeters over here and it's a positive value, we know that this is in towards the right. So therefore it's to the right. Okay, so that means in terms of, we look in terms of this picture over here, that is 11.5 millimeters to the right. So this is our left-hand side of the vehicle, that's our right-hand side of the vehicle when we're looking from the top. So that means 11.5 millimeters to the right, and if we had to measure that, that would be probably something that is not an accurate scale, but you be able to identify what's happening over here. That would be that distance over there, which would be 11.5 millimeters. Okay, so we know these are these two lines intersecting. We know that the center of gravity will be at that position. That's looking from the top. The problem comes in if we have to now look at in terms of, let's say, the rear view. We know it's 11.5 millimeters to the right. So again, that would be roughly over there. So that distance over there would be 11.5 millimeters. but how high is it on the vehicle? And that's what we need to then calculate next. Okay, so the height in terms of this center of gravity is now not as straightforward as one would have done it in the previous examples. It now becomes a little bit more difficult type of scenario to take into account, or different calculations. So the first thing we've got to do is we've got to determine what is the angle of this wheelbase. Now, in terms of when the vehicle is lifted up, what's the angle of this triangle in terms of the amount of the angle it's been jacked up with? So we know at the moment we've got a wheelbase distance over there. So essentially we can draw a triangle and then do a calculation. So we've got some triangle, that's theta. The hypotheses of the triangle, that is essentially our wheelbase over there, and that is then equal to 2.470 meters. The height of the triangle over there, or that we're able to determine, we did the calculation over here. That was at 545 millimeters. We subtracted the 165 millimeters in terms of the axle height, and that left us a value of 380 millimeters. Okay, so now that we've done that calculation, we essentially need to now determine what's the angle. So sine theta multiplied by the wheel base is equal to the height raised. So in other words, we can say that therefore sine theta is equal to 380 millimeters. We divide that by 0.380 meters, because we've got to keep our numerator and denominator in the same units. And we divide that by 2.470 meters over there. Okay, so when we do that calculation, we calculate the value of theta. It implies that theta is equal to 8.849 degrees. Okay, so as you can see, we jacked it 545 millimeters high. And to jack up a vehicle this high is quite a substantial amount. With jacks available, especially that you have, and that amount only at an angle of 8.849 degrees. Like I said, we wanted to get 15 to 20 degrees, but that wasn't possible. So at least with this now, that this was sort of the angle we were able to jack it up. It's not going to give us exactly the right answer, but it's good enough answer for us to obtain. The next thing we've got to do is we've got to calculate what the front axle mass change is. For that, that's equal to the total front mass minus the front raised mass. So in other words, we look at the total mass when the vehicle is with all four wheels on the scales. And in the front raised mass, that would be looking at the situation where we've got the rear end jacked up and only those two values are obtained. Okay, so we subtract that from each other, and we only look at the absolute value of it. So sometimes you get a negative value. We don't mind, we don't care about it. We just want the absolute value of that. Okay, so in this case, that's equal to the total front mass. So we've got given as 319 and 340 kilograms. So that is 319 plus 314 kilograms, and we subtract the front raised mass, so that is equal to the two values that we got over here, which was 332 plus 343 kilograms. Again, the absolute value that we're trying to obtain over there. Do that calculation and you get an answer of 16. Actually, it becomes negative 16, but the absolute value of negative 16 is 16. Okay, so now that we've got this value, the next thing we need to now determine is the center of gravity height. And this is calculated by taking the wheelbase distance, multiplied by the front mass change, which we've just calculated over here to be 16, divide by the total mass, multiply that by tan theta. So that's equal to our wheelbase, which we are told is equal to 2.470 meters. Okay, so 2.470 meters. We multiply that by the 16 we've just calculated over there. We divide it by the total mass, which is 1,054. Tan of theta, and theta we calculated to be 8.849 degrees. Okay, and when we do that calculation, we get an answer of 214.8 millimeters. Alright, so now that we've got this answer in terms of center of gravity, keep in mind this is center of gravity from the axles of the vehicle. So if we want to know how high the center of gravity is above ground, we need to then therefore add the axle height. Okay, so the center of gravity height position above ground, that would be then equal to the axle height, and we calculate that to be 165 millimeters. And we add the center of gravity height, which is 240.8 millimeters. Okay, and that gives us an answer, if we round it off, to 406 millimeters above ground. Okay, so if we look at our diagram over here, that would mean 406 millimeters, so if the wheel is 30 millimeters over there, that means that 406 millimeters would be roughly above, well, a little distance above the wheel. So we would probably estimate it's going to be about over there. That would be a distance of 406 millimeters. If we look at it from in terms of the vehicle looking from behind, 406 millimeters would probably then be roughly over there. Okay, so that would be 406 millimeters. And then, therefore, those two lines are intersecting over there, so our center of gravity will be located roughly over there when looking at the vehicle from behind.
Modern vehicles have got onboard telemetry, where the computers are able to record from different sensors within the vehicle, different parameters. What are some of the sensors that and readings that are being recorded, and how are they valuable when you have to evaluate an accident?
So one of the first things we need to say is that the manufacturers don't traditionally install any devices in the vehicle that are, so to say, black boxes with the intention to particularly record. However, on the modern vehicles where we have things like speed wheel sensors, which are measuring the rotation of the tire or the wheel, or we have a steering angle sensor, or for instance we may have a delta V sensor, change in velocity sensor. All of these parameters that are measured by multiple different devices on the vehicle also provide us with measured, quantified values from the vehicle. As an example, we would very often look at a wheel speed sensor. So we could see at certain time frames what rotational speed the wheel is doing. We can relate that back through gear ratios and come to speed ranges. There may be modules in the vehicle, like an engine module that is monitoring the particular parameters of the engine. There may be a gearbox module which is monitoring particular rotational parameters or force parameters in the gearbox. There may be other modules, for instance, airbag control modules, which monitor forces applied to the vehicle and then in turn would activate your seat belt or your airbag. So there's a massive volume of telemetry in general, measured values on the vehicle that are hugely important to us if we can get access to those.
And there's obviously sensors like, for example, like you were mentioning in terms of the seatbelt being on or not, and you'll be able to know if there's a person that was actually sitting over there in terms of the weight that the person is with, and the seat will be able to identify where the different passengers were sitting. So all that type of information would be actually helpful to be able to know in terms of the scenario that that accident was, or that vehicle was within that accident.
Correct. So it may not necessarily be a measured, quantified value, but it may be a measurement in terms of, it may just measure an occupant being present or not. It's still a form of a measurement or a trigger or an activation, or it may actually be a measured value. For instance, you may have a particular sensor that could actually measure the weight of somebody seated in a seat, or as I mentioned earlier on, an actual steering angle. It could quite accurately measure the actual rotational degrees, value of the steering. So there are many factors that are measured and very important.
Cell phones that we get these days have actually got a lot of sensors as well as cameras within them. How are some of these features being used in your job when you do measurements for accident investigations?
So the first thing I will say is that yes, absolutely, modern cell phones are brilliant. They have a lot of apps and a lot of functions on them. Some of the really fancy ones actually have laser distance measurings. Some of them you can actually put the cell phone down and it will measure the angles, tilts, degrees. Some of them will tell you north points, so we can use all of those. For instance, if we have an accident that occurred on a gradient of a road, we could put the device down and it would give us a reading of the degrees or the angles. We can even use the cell phones to take photographs. Some of the cell phones actually have GPS position recording, so we can even say when we've taken that photograph, that's the exact GPS coordinate that we were at. However, I must say that most of the cell phones are not scientifically calibrated, so one needs to caution that if you are using that needs to be able to be validated or checked. However, that said, we have also used cell phones extensively and checked the values in the degrees against actually scientifically calibrated devices, and we found that the cell phones are very accurate. So yes, extremely helpful tool, lots of functions on there that can be used and are great tools to use.
If I should be in an accident, what would be the key things that I should record that would help you in the investigation of the accident?
Good question. So in terms of measuring, remember the principle of measuring is everything that we're going to come back to in the crash. Whether we're going to measure a distance, we need to know what we are measuring and where we're measuring it. And the reason I say that is because that then comes back to what you should do on an accident scene. And the key issue is to photograph everything. Photograph your vehicle in the context of the damages to your vehicle. Photograph your vehicle in the context of where it is positioned and something in the background or foreground that after the fact I can position that. That is so that I can come back and position it if it is moved and measure it. Look on the road for marks on the road, tire marks, positions of various factors. So in essence, photographing everything around in context of something in the background or the foreground or other objects that allow me to look at those photographs and allow us to position items to come back to that principle of measuring, so that we can measure distances between objects and work things out.
And then obviously I would assume that if you have got a GPS location as well, that you can get that value from your cell phone, that will also be useful for you to know then where to go. Okay, but now there's also other factors that are involved in terms of things that are commonly not thought of. So for example, in terms of registration numbers, in terms of the license discs, and those things, maybe even the driver's license of the different people involved in the accident, it would be quite crucial to be able to follow up afterwards with the different parties involved. Are those sort of common things that you've come across that are often forgotten, or that and maybe other factors that need to be considered when and recorded when an accident should happen?
Quite correct. So once again, as you mentioned with the issue of a cell phone, nowadays it's very important to try not to drive with your cell phone in your cubby hole or your center console, so that if you are involved in an accident, your cell phone is in your pocket and you know where it is. The reason for that is it's once you can get out of the vehicle, you can then get out very quickly and easy, take a photograph of the license disc. The license disc straight away gives you the engine number, the chassis number, the registration number. It gives you all of the details you need in one point. Another factor as well is when you're taking photographs around, take a photograph of who the other driver is or the other parties that are involved if you can, because all of those things, someone may tell you something, you will either forget it because it's a traumatic experience, or if you've written it down, you may lose that piece of paper, or you may not understand what somebody's saying and have written that down incorrectly. If you can video record something or photograph something, you've almost got a permanent record of everything. So once again, yes, all those factors, try and photograph or video record everything.
We were able to place the vehicle pretty closely to where they were. We determined that this mark here was from the front right tire of the VW.
So road markings are quite important for you to be able to identify how an accident happened, and it assists you with the analysis that you then perform.
Absolutely, it's actually part of it. Without road evidence, we've basically, you got evidence from the road, evidence from the vehicles. Those are the two main things that we use.
Accident investigation is often considered to be vehicle accidents, yet there's a lot of other type of different accidents that we've investigated in the past. What are some of them that you can sort of recall that would be considered as accidents?
Quite correct. So generally when you refer to the term accident investigation, by the nature of the catastrophes that happen on our road, people associate it only with automobile accidents. But in fact, quite correctly, as you point out, we've dealt with a lift incident, an actual lift in a building. So for instance, where a cable may have failed, or something has caught a light, or a switch has failed and it's caused some sort of problem in the lift, and the lift has perhaps fallen or won't open. So those are, if it's more serious and something catastrophic has happened, that's also a level of accident investigation. The same principles of investigation apply. Looking at everything, measuring everything, photographing everything, analyzing everything. As a further example, we've done some work in the harbor where, also perhaps automobile related, but one of the container carriers that picks up containers has been moving a container around, and an incident has occurred. It's a similar principle where you would analyze the scene, analyze the evidence on the scene, look at the container, look at the actual machine itself as well, all the necessary measurements and evaluations. A further one we've done was a forklift in a factory environment. The forklift was operating up at its limit, picking up very heavy liquid containers, and the shelving and container it was picking up was bumped and not loaded correctly. It caused a massive pushover of a whole lot of shelvings, lots of damages, injuries, a fairly serious incident. You start looking at things of the operator driver training, you start looking at the machinery, you start looking at the object actually being collected, lots of different calculations, lots of different measurements, lots of different evaluation.
Accident investigation sounds like a really interesting job and sounds very exciting, but I'm sure there's a lot of traumatic or sad scenarios that you've had to come across.
Quite correct, particularly on the automotive side of things. Very often a lot of the cases that we deal with involve death or seriously disabling injuries, and very often part of your investigation will need to be to talk to the families, talk to the people that are seriously injured. So there's definitely a major human side to a lot of the work that we do, although primarily we deal with the technical side, which is very interesting. and quite dynamic most of the time. There's definitely a big human component to it. Also, something that needs to be remembered is that your evaluation and your consideration of these cases generally can very seriously affect somebody's life. It can affect whether they go to jail or not, or whether they lose their job, or whether they may get a payout or not. So there's a very serious human side to the work that we do. What should also be remembered is a lot of the work that we do, although there's a huge component out in the field, there's a greater component sitting in the office behind the desk, actually compiling the reports, actually reviewing the evidence, and that is the not so glamorous side, the side that you don't see, that's not televised in glory like a CSI program. So yes, there is a big human side to the work that we do.
Now, when it comes to accident investigation, there's obviously different disciplines that get involved with this type of work, and it's a continuous learning process that you've got to do. Can you give us a couple of examples that you've had to come across that would require you to learn new concepts, maybe get involved with different disciplines that would actually be involved with the investigation of a certain accident?
Quite correct. So as a prime example, as we see exactly with this device, this is a total station, and the total station originally was used in the civil engineering realms. And it's typically used in civil engineering and construction, and it's used particularly to measure and to position. It's been adapted across to our industry, which allows us very accurately and conveniently to set up at one point and fire and measure. So for us, we could go the old school method of measuring through principles of triangulation, measuring positions manually with a tape measure. We've had to adapt from the civil and construction engineering to use this particular device. A further, perhaps very common piece of knowledge you would need to know is that tires are extremely important in the automotive realm of accident investigation. So your level of knowledge on tires has to be very, very good. How do you measure tires? What are tires about? What effect do they have when they're in good condition or poor condition? What effect does that have on vehicle stability and handling and braking? So there's a lot of cross-pollination to other aspects. As I've said, the total station measuring, tires, understanding that. Perhaps you may even need to delve into learning and understanding issues of metallurgical engineering in terms of part failures, in terms of bulb filament analysis. You may receive a lot of training in that and know a lot about that, but you may call in a specialist in that particular realm. So yes, very diverse, a lot of other factors, and it's particularly in the modern day vehicles, exactly as you said, electrical and electronic engineering in the modern vehicles with the modern telemetry and bus systems in the vehicles, very, very important.
In any crash investigation, one of the most important things is the tires, especially when there's wet weather involved. The dispersion of water from under the tire is reliant totally on the channels, which are the main channels that we see here. In each one of these channels, they have what is called a TWI, tread wear depth indicator, which is the little nipple that fits in between each one of these channels. That little nipple is the minimum required height by the OEM, by the manufacturer of this tire. Once your tire reaches that little tread wear depth indicator, the tire is then illegal. The fallback within the National Road Traffic Act is 1 millimeter if the tire does not have the tread wear depth indicator. If there is a tread wear depth indicator, that is your minimum requirement. Right. So what we would do when we measure the tire, the very first thing we would do is we would take chalk and we would just make a little bit of a surface across the tire. The reason we do that is because when we're taking photographs, it makes the channels stand out nice and proud in the photographs. That's the only reason we do that. You can see it very clearly. These little lines on the side here are referred to as sipes. Even in the National Road Traffic Act, you have to be able to see those sipes. They may not be worn away to the point where you cannot see them anymore. Nonetheless, you can measure these channel depths either with a typical normal measuring device, which is a vernier. I tend to prefer using the vernier. However, there's various different little tread wear depth indicators that you can purchase. But in essence, you need to make sure that you measure the channel square and flat, right angles 90 degrees with the channel. Obviously, you get your error if you are measuring at an incorrect angle or incorrect tilt. So it needs to be square with the surface, and obviously you would push your little reader down into the channel. And so, for instance, on this vehicle, we have an outer channel depth at 2.66 millimeters. That's the channel depth on that tire. You would do the same square and true on each one of these channels, and you would measure each channel. You would measure it in line with the valve at your 12 o'clock, 3 o'clock, 6 o'clock, and 9 o'clock, so that you know your readings the whole way around the tire. Ensuring that the gauge is 90 degree and evenly flat across the channel. And taking the little reading down. You can see the little nipple is extended into the channel, and it's giving me my reading of 2.98 millimeters deep. Okay, so one of the most important things we do in any crash investigation is literally measure, in what's known as layman's term, how rough is this surface. The relevance of that is that in any application of any calculation, you would need to know how rough the surface is. So you would typically appoint a factor for a good condition road of 0.7, 0.5, 0.8 mu, which is your coefficient of friction reading. You can use advanced electronic equipment to do your reading, but from a very, very basic principle, you can take a known mass. What we've done here is we've taken a quarter section of tire. We know the mass is 13.5 kilograms. We've previously weighed it. The device itself is center of mass. In other words, what we've done is we've used cement. But before we've used cement, we've filled it with water. We've taken 50% of the water out. We've drawn the line. We've put our pull point on the center line so that we know we're pulling exactly even along the center of mass. We know the weight of the mass through application of very simple mathematical calculations. We can pull this mass, and through taking a reading on a normal scale, we can then apply the necessary calculations, and we can determine a coefficient of friction for this. It's not necessarily absolute accurate, but it gives us a close enough indication, and we can also do the same test by doing a skid test or using other electronic equipment. But in very simple principle, all we would do is we would take this known mass tire, we would make sure we pull level to the center of mass of the actual device, the actual object. And as we pulled it, we would take a reading off the scale. So in this particular pull, we could see straight away that we ended up with approximately 11.5 kilograms pull force in order to move that scale along this surface. Alright, so for the exact reason of trying to get a more accurate and reliable reading, generally we would take 3 pulls with one scale, 3 pulls with another scale, and 3 pulls with a third scale, and then across all 3 of those average that. That's for the process of repeatability. And then obviously once we do the skid test, and if we use electronic telemetry to do a further test, we would look at all of those individually and then average across all of them.
A radar gun works in a very similar way as what a total station would work. So it still sends out a signal. The signal is bounced off an object and comes back. And at the time of flight, that signal is recorded. So in other words, it's being looked at how long it takes for the signal to get to the object, reflect back and get back to the radar gun. So what we're going to be basically doing with the radar gun though is that it keeps on doing that recording to be able to know what the distance is. but in this case it's actually looking at the change in distance over time, which allows us to be able to identify what the velocity is of the vehicle. We're going to be doing this test now with the vehicles in the speed. So this identifies the vehicles at the speed of our travel. We are next to a freeway over here, and we are able to measure the speed of the vehicles as they pass in a freeway. But it's crucial to be able to take the measurements straight ahead of the vehicle and not at an angle, as that would give you different readings. So as you can see over here, we're busy taking readings of the vehicles as they're passing, and it's giving us about 28-30 kilometers per hour. But as we are moving across, we will see that we come more and more in line with the vehicles and the speed increases. That will give you a more accurate reading. The problem is that you have to be up front, in front of the vehicle to get an accurate reading. Otherwise it can give you inaccuracies in the speeds, and therefore the fines won't be appropriate. The radar gun is able to pick up the speed that the vehicle is actually traveling at, this specific vehicle, 120 kilometers per hour at the moment. As we're busy passing a vehicle, you will see the speed of that will be the difference between this vehicle and that specific vehicle. 46 kilometers per hour, that we are going faster than that was. Would you say that in your career it was a situation that you had to go and just study for a couple of years and know what's happening, and then after that you never had to study again? Or was there a need for you to continue learning new stuff, attending new courses, and getting familiar with the latest technology?
Absolutely, very, very important question. In any field, you can go and do the basic training, the basic studying, and you are trained up to a basic level. You will never, ever, ever remain on top of your game or on top of developments unless you further your studies. Whether that be a casual one-day course introducing you to new methodologies or new products, whether that be an intensive 3 months, 6 months, year-long diplomas or degrees, there is a constant requirement for you to keep up to date. One of the things that we do full-time is looking at the latest research papers. So we read in the research realm what is published by Society of Automobile Engineers, what's published on IEEE, what is published worldwide. So an absolute requirement for that.